So hello everyone who's watching the session on YouTube. I guess I'll get started in like 5-10 minutes, just waiting for a few people to join the session in person. So yeah, maybe I'll get started in 10 minutes. Okay, so I guess since no one is joining the session in person, we can just get started nonetheless. Yeah, so hello to everyone who is watching on YouTube. So just to reintroduce myself, I'm Lakshya Sagi, the problem solving TA for the NPTEL Social Network Analysis course for the Monday 6 to 8 p.m. sessions. This time around, we are having the session on like Tuesday 6 to 8 p.m. because of some like reasons, like because I had some work yesterday, so I could not take the session yesterday. But from next week onwards, again, we'll be back to Monday 6 to 8 p.m. timings. So again, like in this week's session, we'll be covering like again like first we'll be covering the summary of like all the topics which are discussed this week. So which was mostly on like link predictions and all. So missing link prediction and like future link prediction, and then I also have some problems prepared so that we can discuss the problems after we have gone through the summary of the topics covered. So yeah, so maybe I'll just now share my screen and we can get started. So let me just share my screen. Okay, so I hope my screen is visible since there is no one in the meeting right now, so I don't have someone to actually verify this. But yeah, let's just let's just get started. So, as I already told, that this week's topics are mostly about like link predictions in graphs in basically social networks. And yeah, so first of all, what is link prediction? So, link prediction, as discussed in the lecture, is nothing but like the problem of predicting existence of a link between two entities in a network. So you want to predict whether like okay, so if you're given some part of the network, then like does there exist like suppose you have only partial information about the network and you want to know like what will the complete information of the network look like. Suppose you are given a maybe subgraph of the original graph. This is the subgraph of the original graph, and then you want to know maybe like will Adam and Sophia also have an edge between them? Like, what's the probability that Adam and Sophia will be having an edge between them? So yeah, so this is essentially a list missing link prediction, and yeah, and it like so there are like two kinds of link predictions here. I'll come to that maybe later, but on high level, like so you can predict like okay, like maybe I have some partial information about the graph right now, and I want to know okay in this graph only maybe did Adam and Sophia have an edge or not. Like I want to predict did Adam and Sophia have an edge or not, and it's just that uh, I missed that information. And another kind of link prediction is okay, I have complete information about like this graph at time t. So at time t, this graph looks like this. So maybe at time t plus one or sometime later, what's the probability with which Adam and Sophia will have an edge between them? So, yeah, so these are the two kinds of link predictions which are primarily studied. Like one is called future link prediction, where you completely know about the present, and then you have to know about the future. And then there is second thing is missing link prediction, where you are told that you're only given like maybe partial information about the present, and you have to figure out what the complete information might look like. So yeah, so so in general, so all of these are motivated by like like mm, changes in network. So why do we need all these link predictions and all? Because like these social networks by nature are dynamic. It's not like you're given a fixed social network and it will remain the same. It can change over time, and sometimes like you might not even know about the full information of the network. There are various kinds of things. So so maybe one case is like okay, so let's just see what the temporal changes in the network look like. So temporal changes are basically changes which occur over time. So if you are given like some social network topology at some time t naught, then what kind of things can happen in the future, like after t naught? So one thing can be that new nodes are added, but they do not form any link. Like, okay, case one is maybe just this node D gets added, but does not form any link. Case two is new node comes and then forms new connections. Like this is an example of case two. Case two where like D node comes and it like starts forming connections with A and C. Then case three is no new join, no new nodes join, but some new edges are formed. So like here, no nodes have joined, but in the like, so the nodes are only A, B, C here, but like one new edge can form over time. And the intuition for this is okay, maybe like A and C were friends, A and B were friends. So maybe in the future, like A will introduce B and C, and so they'll also become friends, something like that. So this would be the case of maybe like addition, like the graph is so some vertices or edges are being added to the graph. But case four and five are okay. Maybe like why do we only think about like maybe things being added to the network? Things can also delete over time. So like it might be the case that two people who are friends may unfriend each other after some time, maybe because of like dissimilar interests and all. So yeah. So some existing, so okay, this case for some existing edges are removed, but endpoints are retained. So ABC are still the endpoints, but maybe this AB edge gets removed. And another scenario can be some existing nodes and edges are removed. So like nodes are removed as well as edges are removed. So suppose here like B is removed and then this AB edge is also removed. So only the AC network remains. So yeah. But so there can be like these kinds of temporal changes in network. But what we'll be concerning ourselves is like okay, like all of these are interesting, but for simplicity, like in the scope of this course, at least for this week, we will only restrict the discussions on case three. So the case three is no new nodes will join, but only new edges will be formed. And that's why we are calling it link prediction. We are not calling anything like node prediction or anything. Because we are only predicting whether a new edge will form. Edge can be sort of a link. So yeah. And then there are two kinds of link predictions, as I already told, missing link prediction and future link prediction. So we'll get to that. Like yeah. So first of all, maybe so as I already told, like what is missing link prediction? Like you're given like partial information about the current network, and you need to figure out what will the actual network be looking like at present. Whereas in future link prediction, you are given complete information about the present, and you just want to know about future. So there is a slight difference between like missing link prediction and future link prediction, which is important to know. But like mostly techniques which I use are kind of similar in both the cases because yeah, the measures which you can define for missing link prediction can also be adapted for future link prediction and vice versa. So let's just maybe like formalize this problem of link prediction. So given snapshots of a network at time t equal to t naught and at time like maybe t equal to ti, which is greater than t naught. So you have to predict the set of edges which join during this interval of like t naught to ti. So, so effectively like you want to know like given some time interval how many edges would have joined, how many new edges would have been added in that time interval. So yeah, and which can also be alternatively thought of as the task of determining the likelihood that any two nodes that are not connected at time t equal to t naught will be connected at time t equal to ti. So nodes which are not connected right now will be connected in the future. What will be the probability? And this is what you call the problem of link prediction. And like this can be thought of as finding needles in a haystack because like suppose the graph is very huge and you have to find out like some whether some specific link will form or not. So since the graph is huge, like it is like equivalent to saying that you have to find, mm, yeah, analogy can be like you have to find needles in the haystack. So yeah. Okay. So before coming to like what actually is a good link, like what actually are the good algorithms for uh, link prediction, the more important thing is like evaluate. Like first let's just get to like how do you evaluate, how do you even evaluate the suppose you already have some algorithm A which helps you in link prediction. How do you evaluate the performance of that algorithm even? So it's a good idea to maybe have the end goal in mind, like what do you want to optimize, or what do you want to optimize our algorithm over, and then get to the algorithm, like what kind of algorithm will work for what objective. So first, like let's just define what kind of objective are good objectives. So there are multiple methods for link prediction, evaluation, and like so one thing is like training test split. So here what happens is like okay, so you're given a single snapshot of the network, and then you want to see whether your link prediction algorithm does good or it does not, it does badly. So what one can do is maybe like as is done commonly in machine learning. So if you are given some data, you divide the data into maybe some training data. Even though you have like labels for all the data, you still divide the data into like some training data and some test data. And then what you do is you train on the training data and then like test over the desired metric on this test data. So the data here is like nothing but the edges or the links, because we want to predict some links uh, subject to we are given some links. So what one can do is just maybe select some random edges from the network and put it into the test set, and then for the remaining edges just train the model over the remaining edges, and then test whether your model does good or not. But there can be multiple deletion strategies, like how do you even pick this test edge, uh, the test set. So what one can do is maybe just pick uniformly at random some of the edges from the given network, and then just delete those edges and put them in the test set, and then check whether like training one can do good by training over the remaining edge set. But maybe like this is not the best idea always, because what usually can happen is, suppose there are some very high density clusters in the network. So there is a high probability that if you are sampling uniformly at random, some of those edges will also go into your test set. Many of those edges will go into the test set. And note that the edges which are present in like highly dense clusters are very easy to predict. So this was discussed in the lecture also, that edges in the highly dense networks are easy to predict. So any algorithm will probably do good on this kind of a test set if you have just like picked out edges from like high density clusters. So the real problem is uh, checking for like so the real difficulty of this problem lies in predicting the edges which are like very far apart, or maybe the edges which are more bridge like. The edges which are somewhat more far apart and do not lie in the same clusters are much more difficult to predict, and that's the meat of the problem actually in this link prediction method. So usually like sampling uniformly at random for the test set is not a good idea. It's better to maybe do it sampling based on some more topological constraints, like maybe degrees of the endpoints, or yeah, something like that. So yeah. So anyways, like in the task of inferring missing links as well as task of predicting future links, the train test split methodology remains the same. Like uh, in predicting future links, just takes a subset of edges of the present which you are given, and then try to predict the future from those set of edges, something like that. So yeah, and then yeah, so what one usually does is maybe like divide your samples into like positive and negative samples. and what do we mean by like positive and negative samples. So yeah. So what can happen is so by what do I mean by positive and negative samples? On a high level, like a positive sample is a sample like maybe which has an edge between it, and the negative sample will be the pair of vertices which do not have an edge between them. So like just maybe like formalizing this notion a little. So suppose you are given some original network at times jam t equal to ti, and like the number of set of all possible edges in the network is obviously 2 raised to the power e. So this is the power set of e, and then you divide this into like a training set and a test set. Like, so you're given this initial network, so you divide this network's edges into like training and test things, and then so the set of edges which are not formed till timestamp ti is maybe what you say is the set of edges which are not formed till timestamp ti is like u minus the training edge set. So these are the set of edges which are not formed till timestamp ti, because like what you're trying to do is yeah, you are divided your like you split your current set of network into like some testing as well as training split. So now you'll only deal with training split while like doing some algorithm, and then predict it on the test split. So now what we have is we just have a binary classification problem. So the edges which are present in the test split are the positive samples for which you would want to predict an edge, and then the edges in this L minus E test sample are this L minus E test set are the negative samples. And what this means is yeah uh, so these are the edges which actually don't have, like these are the pairs which don't have an edge between them. And note that positive samples are expected to have higher probability than negative samples. Okay then. So yeah, again like still continuing with evaluating link prediction methods. So many of you would probably already be familiar with what is a confusion matrix, since this is like a pretty common concept in machine learning algorithms, and like we discussed this anyways in the last week's session also. So like we discussed like so there are like, so what we have is predictions, and what we have are some like actual things like, so this is the ground truth. Like so if we have like on horizontal axis we have the ground truth, and on the vertical axis we have the predicted values. Then like true positive is like if actually link was there and you predicted link was, and your model predicted link was there. So a false positive is like your model predicting it as positive, but actually it is false, so actually there is no link. Similarly, what's a true negative? So your model predicts that it's negative, and your model is true, so the link is actually not formed. And yeah, so and what's false negative? Your model predicts negative, so your model was wrong, so actually the link should be formed. So yeah, so this is like this classification we discussed last time also, like what are true positive, what are false positives, what are false negatives, and what are true negatives. So yeah, so these are just like, and this matrix, if you form the matrix like this 2 cross 2 matrix is also known as the confusion matrix. And this is not like a specific to just graph or like social network analysis. Like this confusion matrix is used maybe across like whole machine learning or whole learning theory domain. So yeah. And yeah, then there are some parameters which one can associate, like to assess the quality of your predictions. Like, so one usually uses this confusion matrix as a benchmark, and then maybe define some formulas over this confusion matrix, which quantify like what how good is the quality of predictions. Like in this binary classification problem of like predicting the test edge set, and like not predicting the pairs of edges which are not actually not present. So this can be thought of as a binary classification problem, and then you have a confusion matrix,
And then to assess the quality of the classification or your prediction algorithm, there are numerous kinds of metrics defined. So one is accuracy. So some of these we discussed last week also, but maybe we'll just go over them again. So what is accuracy? So accuracy is nothing but total number of correct predictions to the total number of predictions. And note that what are total number of correct predictions. So total number of correct predictions would be the predictions where model predicts true and it is actually true, and model predicts false and it is actually false. So true positives plus true negative divided by total number of predictions, which should just be true positive plus true negative plus false positive plus false negative. So this is accuracy. So accuracy, and then what's precision? So precision is like out of all the links that are predicted by the model as positive, how many actually belong to the positive samples? So uh, what are the links? How many links are predicted positive by the model? So the total number of links predicted positive will be like a number of true positives plus number of false positives. This is the denominator, and how many actually belong will just be true positive. So precision is nothing but true positive divided by true positive plus false positive. And then what's recall? So recall is out of all the links that are actually positive, how many are predicted as positive. So so number of links which are actually positives will be just true positives plus false negatives, and then how many are predicted as positives will be just true positives. So recall is nothing but true positive divided by true positive plus false negative. So note that it may seem like if you are not familiar with all of this, it may seem like we are throwing a bunch of terms around and a bunch of formulas for calculating them, and it's not like clear like why do we need so much formulas? Like why is not there a single metric which does everything? So maybe we'll address some of that later in some of this was addressed later in the lectures. So maybe we'll cover that also. But on a high level, like I think you can see from the different definitions like what all of these things actually like intuitively correspond to. So accuracy tries to show like with what so the accuracy metric is like corresponds to uh, saying that with what probability will your model make the correct prediction. So what's the probability with which the model will make the correct prediction is what this suggests. But note that you don't necessarily always need your model to just have high probability of correct predictions. You also want some kind of fairness that okay, the model should not okay, even if the model has good correct predictions, it should not be the case that model is skewed towards maybe like positive predictions or negative predictions. Like it should not be the case that the total number of correct predictions are all coming out from like the model being always correct on positive instances but never being correct on negative instances. So if that's the case, then maybe still like accuracy can be high. But if the model is always correct on positive instances, but never correct on negative instances, uh, then like some of these other metrics can be like precision or recall can be bad. And yeah, in that case, but what you usually want is all of these metrics to have like good values, because you want your model to like even though it should output good, it should have good accuracy, so its output should be like reliable, but also like it should be the case that if it predicts positive then also it should be reliable, if it predicts negative then also it should be reliable. It should not be the case that yeah, it's only reliable when it predicts positive but not unreliable when it predicts negative. So, yeah. So that's why you need like all of these kinds of terms. So precision, recall, and similarly, so there are some further terms like there is this true negative rate, which is also quite useful, which says that out of all the links that are actually negative, how many are predicted by the model to be negative, which I kind of just described. Like similar to this, something I described. So out of the, and this is also called true negative rate is also called specificity, and so its formula is just so the total number of links that are actually negative will be just uh, like true negatives plus false positives. So denominator will be true negatives plus false positive, and then how many are predicted by the model. So the predictions by the model are like just true negative. So this is like true negative rate, and similarly one can
define something called false positive rate, which is also called like false alarm ratio or fallout rate, which says that out of all the negative samples, how many are predicted wrongly to belong to the positive class instead. So, so what are the total number of negative samples? Total number of negative samples is nothing but true negatives plus false positives, and then how many are wrongly predicted to belong to positive class instead. So the wrong prediction is nothing but number of false positives. So effectively, like, so what you can see is like true negative rate plus false positive rate is equal to 1 actually, like Tn plus Fp. So if you just sum like, so it's usually like easy formula to see that true negative rate plus false positive rate is actually equal to 1, because the denominators are same, true negative plus false positive, true negative plus false positive, and after adding all of both of these, you get true negative plus false positive in the numerator. So these cancel out and become equal to 1. Oh, so Karpagam has joined. Okay, I did not notice so. Hi, Karpagam. So I have. So is my audio clear, Karpagam? So yeah, hi. So I was just. I had started like a session. I had started explaining the session, and like so I was just going over the initial like the summary of like the lecture. So we just maybe finish summarizing like first lecture of this week. So so basically, what is link prediction? What do we mean by temporal changes in a network? And then like how do we evaluate link prediction methods? And we were just discussing about this like what's confusion metrics and the different kinds of like mm, metrics or like different kinds of values which you can obtain from confusion metrics, which would be yeah, which are useful for us. Okay, no worries, Karpagama. Like, if you think like there is something uh, which you need to revisit, like, anyways, we upload these lectures on YouTube, so you can go over them. But otherwise, like, yeah, uh, we can like continue from here. So right now, I was discussing what is accuracy, what is precision, what is recall, what's the true negative rate, and what's the false positive rate. And then like another thing which I was discussing was one important thing is why do we have so many formulas and everything? Like, so we are given one confusion matrix, so why just not like look at accuracy and say, okay, if accuracy is good, our model is good. But note that we just don't want our model to be accurate. We also want to be in some sense fair. So maybe what can happen is your model always predicts the positive instances correctly, but never predicts the negative instances correctly. So in that case, also the model may then end up resulting in having like a good accuracy, but then one of these precision or recall will be bad because like your model only works for positive values but not for negative values. Whereas you want your model to be reliable over both. Like you can sacrifice some of the accuracy as long as your model predicts correctly on both positive and negative instances. So yeah. So yeah. So for example, so there was this kind of an illustration discussing the lectures. So maybe like we can skip over this because yeah, I think I just so what you so suppose like you have some kinds of predictions and you have the actual data and then you have to find out these kinds of values, the accuracy, true negative rate, false positive rate, and so on. So it's just easy exercise to do using these formulas. And yeah. Oh, okay. You couldn't understand this illustration, Karpago. So should I go over it? Okay, okay. So okay, then maybe I'll go over it. So I think we discussed what is true positive, true negative last time also, right? But I'll just go over them again. So, so maybe I'll just let's just get to the theory first again, like, and then maybe yeah. So, so like this is the confusion matrix, and this denotes what are true positive, what are false positive, what are false negative, and what are true negatives.
So as I said last time, so the best way to look at it is like, what do we mean by true positive? Or maybe let's say, what do we mean by, yeah. So what is meant by true positive? So like, so note that like, so all of these terms like true positive, false positive, all of these things have like two words. Like first word is like either true or false. The second word is either positive or negative. Okay. So the second word actually denotes what does your model predict. So whether your model predicts positive or negative will be denoted by the second word, and whether that prediction is correct or not will be given by this first word. So if it is true and it is positive, it means like it's, so what the true positive means is like, so how I look at it is, so I look at the second word first. So I say, okay, so positive. So this means like I have to count the so I have to take into account the predictions which were predicted as positive, and out of those I have to count the predictions which are which were where the prediction was actually true. So it means like it was predicted to be positive, and it was indeed positive. So actually also in the ground truth it was also positive, so link was formed, and prediction was also that link was formed. Similarly, if you look at this term, let's say false negative, so what does this mean? So for false negative just means that your prediction was negative, but your prediction is also false. So if you predicted false and if you predicted negative and it is false, so it means in actual ground truth it should be true. So that's why like in actual ground truth it should be positive. So that's why like in actual ground truth link is formed, whereas your prediction would be that link is not formed. And similarly, you can think of these two also, false positives and true negatives. So does this high level idea kind of make sense, Bhagav? Like, how do you think of these uh, true positives or maybe true negatives, false positives, false negatives? So at least I like to look at it this way. Like the second term denotes what your prediction was, and the first term denotes like whether that prediction was indeed correct or not. Okay, okay. So you found, okay. So then maybe we can move on to the problem. Yeah. So I'll just move on to the problem then. Uh, to make it a bit more clear. But I hope like at least the high level idea was clear. So okay, so now let's just maybe find out the number of true positives. True. So here like what the problem states is yeah. So so in this diagram, what the diagram is saying is that uh, so suppose this is a graph given to us. So this is the graph which is given to us. Like so, there are four nodes A, B, C, and D, and actually in these four nodes only the edges AB, BC, and CD are present. Whereas what our model predicts, our prediction is given by this dotted line. So our model predicts that AB, BD, and BC are present. So let's just see maybe like what edges are actually present and what edges are actually not present. Okay. So what do we have as true positive links? Or maybe like, okay, like let's just look at positive links and actual negative links. So let's just look at the ground truth first. So ground truth is that AB, BC, and CD are positive. So actual positive links are AB, BC, and CD. And what's the predicted positive? So our prediction says that AB, BD, and BC are positive. So these are positive. And what will be like negative? So actual negative links will just be the pairs which don't have an edge between them. So in the original graph, like in this actual graph, like there is no edge between A and C. Similarly, there is no edge between A and D. Similarly, there is no edge between B and D in the original graph, even though it is there in the predicted graph, but it is not there in the original graph. And yeah, so I think only these three will be the edges. So AC, AD, and BD. These are the actual negative links. So AD, AC, and BD are the actual negative links. And similarly, like in predicted positive links, we had AB, BD, and BC. So the remaining pairs will be actually predicted negative. So like AC does not have a predicted edge, so it is negative. AD is also negative, and similarly BC is negative, and CD is negative, if it makes sense. So AD, BC, and CD are actually negative or predicted negative. So does this make sense, Karpagama? Like at least like actual positive, like we have not yet discussed what are true positive, what are true negatives, but actual positive, actual negative, and predicted positive and predicted negative. Okay, they are clear. Nice. So now let's look at like let's find out the number of true positives. So what do we mean by true positive? So true positive is actually so the prediction should be positive and it should also be correct. So we have to find the edges which are actually true and were predicted to be true also. So we have to take intersection of these two sets. The set of edges which are actually positive and were also predicted to be positive. So which all edges lie in this kind of in the intersection of these two sets will be like A comma B and B comma C. So these are the two edges which lie in both of these things. Note that B comma D does not lie in this set, only C comma D does not lie in this set. So A comma B and B comma C are the only predictions which are positive as well as true. So that's why like true positives value will be equal to 2. Now let's look at true negatives. So what do we mean by true negative? True negative is the prediction should be negative and the prediction should actually be true. So what this means is that it should actually be negative also and prediction should also be negative. And this would be given by intersection of these two sets, like actually negative and prediction is also negative. So what's the intersection between these two sets? So AD is common between both. A comma C is also common between both. So true negative is just 2. So does it make sense till now, Karpagama? Or are there doubts? Okay, it's fine. Nice. So now maybe let's just see what is the false positive. What are the false positives then? So prediction should be positive, but it is false. So actually on the ground truth it should be negative, but prediction should be positive. So actual negative intersection with prediction positive. So intersection of these two sets gives us a false positive domain. So what are the edges which line both of these sets? So only B comma D is common between both of these sets. If you take the intersection of these two sets, only B comma D is common. So false positive will actually be just 1. Similarly, in false negative, your prediction should be negative, but it should be false. So actually, it should be positive. So you have to take intersection of these two sets, and then only C comma D comes out to be the common intersection point, common intersection edge. That's why false negative is 1. And then finding accuracy, true negative rate, false positive rate, or precision or recall is just like application of the formulas. So note that the only thing where like you have to like be careful is like finding out these numbers: true positive, true negative, false positive, false negative. After that, it's just a simple formula application. So is it fine? Like are all of these now fine? Karpagam? Like what are true negative, true positive, false negative? Okay, it's fine. Nice. So maybe we can uh, move on in that case. So before that, I'll maybe just mute myself for a minute. Like I have to go and uh, yeah, drink some water. So I'll be back in a minute. I'll just mute myself to then.
Hi, so sorry for the pause. So maybe we can move on now. So yeah, again, so this thing I already discussed, like why is accuracy not enough? So I already told you that only accuracy is not enough, because what we want is our model to not be just accurate, but also be good, accurate on both positive as well as negative predictions. So it should not be that the model predicts all the positive cases correctly, but fails on all the negative cases. But thus, like the accuracy turns out to be good. But what we want is some kind of fairness, that so we are willing to sacrifice some of the accuracy as long as like we can predict both positive and negative instances trustworthily. So yeah. So there is an example, you can go over this example, but you'll see that okay, in this kind of model, like accuracy would be 90%, but the model is very bad. So something like that. So yeah, you can look at this model yourself, but the intuition is what I just showed. Maybe I'll just skip this. So then, like, so what we usually have is there are these kinds of ROC curves. So what these ROC curves say is like, so ROC, the abbreviation for ROC is like receiver operative operation characteristic, uh, something along these lines, and yeah, so uh, yeah, receiver operating characteristic curve. So what you do is, so one good measure to see like how good your predictions actually are is to maybe make a ROC plot for your prediction. So you keep your on y-axis you keep true positive rate, and on x-axis you now keep the false positive rate. So you keep the true positive rate on this side and you keep the false positive rate on this side, and then you make this ROC curve, and then you take the area under this curve. So these are kinds of like heuristics, but which are kind of useful to do that. So what these heuristics kind of say is that so if you take the area under this curve, then better the area, we say that the better is the model with compared to a random prediction model. So yeah. So what this essentially says is, maybe we can look at this a bit more. So suppose what you have is this ROC curve is nothing but like you have true positive rate on the y-axis, you have false positive rate on the x-axis, and maybe let's just look at the formulas for this true positive rate and false positive rate. So false positive rate is nothing but false positive divided by false positive plus true negative. Similarly, true positive rate will be just like true positive divided by like true positive divided by true positive plus uh, false positive. If I Yeah, okay. So true negative rate is something like out of all the links that are actually negative, how many are predicted to be negative. So similarly, what will be true positive rate? It will be out of all the links that are actually positive, how many are predicted to be positive. So it will be true positive divided by true positive plus false negative. So something like that. So what you essentially are saying is, so you have this true positive rate on the y-axis and false positive rate on the x-axis. So false positive rate just tells us like out of all the predictions which we predicted as false positive, uh, like uh, like how badly did we do in our predictions, uh, like how many did we wrongly predict to be positive, which is false positive out of all the negative samples. Similarly, true positive rate is like out of all the positive samples, how many did we actually identify? So on the y-axis, it kind of what our model is saying is that out of all the actual positive models, how many did my model identify correctly? And this false positive rate is out of the negative samples, how many of predictions did my model just predict to be positive? And note that so if you take this line like y equal to x line, where the area of the curve under this line will be just half, because it's a triangle with like height and length of base as one each. So this is kind of a worthless model, because this is just uh,
random. This is equivalent to like a random prediction model, because like if you just randomly predict every like, so if you just randomly say that everything is like, if you randomly say okay, like one thing is like, with you toss a coin with probability half, you say that the link is positive, with probability half you say that the link is negative. And if you do that kind of a thing, then you can actually obtain like this kind of a curve for like true positive rate versus false positive rate. So the better our model does with respect to random, we'll say the more good is our model. And note that the best that our model can do is like have like the best that our model can do is like this kind of a curve, like which just goes straight up till one and then straight up goes horizontal. What this means is that the model really does not have any false positive rate while it has some true positive rate. And as soon as it has best true positive rate, then only false positive rate can start increasing. In that case, the area under the curve is maximized. So the best model will have area under the curve as 1, and the better the model will say, the more the area under the curve will say better is the prediction model. So yeah, and similarly, so like so there are different methods as I already said. So like all of these are kind of heuristic based in the end, but these heuristics kind of tend to turn out better. And note that this is not like specific to like graph theory, like social network analysis or something. Like ROC curves are very common in machine learning models also. So yeah, almost all of these are derived from machine learning and everything. It's not like specific to uh, social network analysis. And similarly, there is another curve which is like precision recall curve. And yeah, in this precision recall curve, also, yeah, mm, we plot the like recall along the x-axis and precision along the y-axis. And yeah, so the random predictor uh, is a horizontal line along the x-axis, and then you want to see like how better does your model do as in this kind of a curve. So again, like there are different kinds of ROC curves. Yeah. So and then what are kinds of problems which we have in like evaluating some link predictions? Like what kind of problems do we run into? So uh, one thing is like in link predictions, like obviously the graphs are temporally dynamic in nature, which means that so temporal means like with respect to time, and dynamic means like it changes. So the graphs change with respect to time. So and these changes are very hard to obtain from like real world data. Okay, so we initially said that we'll divide the initial set into like some training set and test set, but yeah, obtaining this training set itself is kind of difficult. And yeah, some edges can get added over time, some can get deleted over time. So yeah, so modeling these temporal networks is inherently kind of difficult. Then like edges can also have some kind of directions where it changes everything. Right now we are just classifying the problem as binary classification where either edge is present or not present, but maybe edges are also directed. In that case, like a UV edge and a VU edge will be maybe weighted differently. Similarly, like edges can have signs, weights, and then size of negative sample is often much larger than that of positive sample. So the edges not present in the graph is usually much larger than the edges which are present in the graph. Because usually real world networks, as we have already said, as we already studied, that real world networks tend to be sparse. So there are only like there are like fewer number of edges present in the real world network than like much fewer edges present than the number of edges which are not present. So there are like some problems in like which we encounter usually while doing link prediction. And note that now like once we are like a bit familiar with like how to evaluate uh, how good is some link prediction algorithm, then maybe we can move on to like actual algorithms. So yeah, what are the some of the algorithms which we actually use in link prediction? So maybe we'll not cover all of these, but some of these will be covered. So there are like some heuristic models which just look at some maybe local or global heuristics and then just predict like, okay, maybe this edge is similar to this edge is not similar to this, and just move on. Then there are like probabilistic models, which are like hierarchical random graphs or supervised random walks, where you actually model the graph as like a probabilistic network and then try to maximize the probability in some sense. And then there are like some more theoretical models like which are based on mutual information and entropies. So this is not covered in this week, so maybe like we'll not be discussing any of this. Like what is mutual information, what are entropies? That will be a thing for the next week. So let's just first come to like heuristic models. So heuristic models is yeah, heuristic models usually try to leverage like mostly the topological structure of the network. So in heuristic models, what we usually try to do is like we try to like take some high level heuristics into account, like okay, what are the number of neighbors, what are the number of common neighbors, what's the total degree, and we try to like somewhat use these kinds of heuristics to check whether an edge will be present or edge will not be present. Again, as we are like familiar with these heuristics, like in like previous week's discussions, like in community detection also we had some heuristic models. So like as you can see, like there can be some local heuristics and there can be some global heuristics, which means like local heuristics are which are localized to some node or like maybe a couple of nodes and their neighbors. Whereas global heuristics are heuristics which look at the graph as a whole and then evaluate whether something is good or bad. So some common local heuristics are like common neighborhood heuristic, which just checks like how many common vertices are present between two nodes x and y. So what you usually have, the problem in link prediction is, okay, you're given any two nodes x and y, and then you have to predict like what are the chances that an edge will be present in between x and y in the future. So yeah, so one of the things can be like looking at common neighborhoods of x and y and check whether like how many vertices are common in the neighborhoods of x and y. Similarly, there is this Jacquard similarity which we have like discussed multiple times, I think, but we'll just cover this again. Then there are like some more interesting kind of similarity based heuristics which we'll maybe go on to cover. Okay, so first of all, like what's a common neighborhood heuristic? So you just take like for two nodes x and y, you just take the number of common vertices, like the number of like, so you take the neighborhood of x, you take the neighborhood set of y, and you just take the intersection and just the number of vertices lying in the common neighborhood of both x and y will be this common neighborhood. Yeah, and yeah, the higher the number of like, so in this heuristic we say that higher is the common neighborhood. So like if two people have a lot of mutual friends, then it's highly likely that the two people will also become friends in the future. That's why they'll probably, yeah, form have an edge in the future. So this is the common neighborhood heuristic. And then Jacquard similarity just tries to like normalize this thing. Like it tries to normalize this by dividing it by union of the two sets. So the common neighborhood divided by union of the two neighborhoods is uh, what Jacquard similarity says. Like this is again like higher the Jacquard. So these are different heuristics. Like so with respect to Jacquard similarity, also like higher the Jacquard similarity, higher is the probability that the nodes will form an edge. So there are some other heuristics like which probably haven't been discussed before. So one is this Salton index. Salton index is so it takes into account not just like the sizes of the common neighborhoods but also degrees of the vertices that which we are using. So the again like the numerator is same, which is like the common neighborhood intersection, but it's divided by square root of k of x times k of y, where k of x is nothing but degree of x, k of y is degree of y. So what you just do is yeah. mm, tau x times tau y, so the intersection of common neighborhood divided by square root of the product of the degrees. Similarly, there is this thing called Sorman index, where instead of taking the square root, so the square root is nothing but a geometric mean of the degrees, right? So instead, if you take the arithmetic mean of the degrees, so numerator is the same always because numerator just represents the number of common neighbors, but you want to kind of normalize it in some sense, and these are the different kinds of normalization factors which I use. So in Salton index, the normalization factor used is geometric mean of the degrees. But in this Sorensen index, arithmetic mean is mm, used as a arithmetic mean is used as a arithmetic mean of degrees is used as a normalizing denominator. And then there are like hub depressed and hub promoted index, which are just like so hub depressed index is intersection set divided by maximum of the 2 degrees of the nodes. So yeah, so the higher degree node is usually called the hub, and here like hub contributes, uh, hub has contribution to edge formation, whereas the non-hub node does not have. Whereas in this hub promoted index, you take the minimum. So hub is, suppose x has higher degree, then x is the hub with respect to y. So y has a lower degree. So now min of kx comma ky will be ky, and then we'll say that in hub promoted index, like uh, the value of this hub promoted index depends on the non-hub node. Whereas in the hub promoted index, the value of the uh, probability actually, or like the value of this hub depressed index depended on the hub node. Here it depends on the non-hub node. So yeah, just a high level idea, but like all of these in the end are just heuristic formulas. So there is really no kind of like very mathematical justification to all of these. These are all like one can just see that okay, maybe like if the intersection set is higher, there is higher likelihood of edges being formed, and like you not normalize it in some sense, and like see that nothing out of these is like the absolute truth. Like all of these are heuristics, and maybe one heuristic is better for performance in some situations, other heuristic is better in some other situations. That is like but there is no mathematical guarantee that one heuristic will always be better than the other. So yeah. And then there's this another heuristic called local heuristic called preferential attachment. And preferential attachment is like nothing but a preferential attachment score for two nodes x and y is nothing but just the product of degrees of x and y. So what the preferential attachment says is that okay, the higher the degrees of the nodes, the higher is the chance that they will have an edge between them. Yeah. Similarly, uh, there is another thing which is like light Hall Newman index, which is just okay. So what we did previously in this uh, so in the Salton index, we took the intersection set and normalize it by dividing it by degree of x, the geometric mean of the degrees. But here, like if you don't take the geometric mean, if you just multiply the degrees in the like normalizing factor, then it's what you call Light-Home-Newman index. Like just the number of common intersections divided by uh, product of degrees. And then there is this another local heuristic which is atomic adder, which is like kind of heuristic. Like if you have to use a local heuristic, like if you are unsure what local heuristic to use, like you have a bunch of heuristics which I already told, and if you are not sure out of all of these which should you use, always start with trying out with atomic adder. Like this is a local heuristic which is kind of like which generally performs better than the other local heuristics. The atomic adder is kind of the one of the better heuristics out there, which has somewhat better performance usually. And what's the value of atomic adder metric between two randomly selected nodes x and y? It's just like 1 divided by log of kz, where the summation is over z is over like the number of like the common neighbors of x and y. So whatever are the common neighbors of x and y, you just say that like, you just take 1 by log of degrees. Sure, Karpagam, I'll just explain the example for atomic adder. And similarly, maybe I'll just cover like resource allocation index also. So resource allocation index just takes, instead of log of kgs, it just takes like one summation of 1 over kgs. This is resource allocation, this is atomic adder. So, okay, so in this network G1, let's just calculate the atomic adder index between the nodes A and C. So this SAA denotes like the metric for atomic adder. This A stands for atomic adder. And then this in the parentheses, we have two nodes X and Y, which is our A and C here. So what you have is like you want to calculate atomic adder index between the two nodes A and C. Let's just see what are these A and C. So this is A and this is C. And you want to find out the atomic adder index. So for this, first we need to find out like the common neighborhood of A and C. So Karpagam, can you tell me like what's the common, what will be the intersection, like what will be this common neighborhood set of A and C? Like what are the vertices which have an edge to A as well as C? This is C, this is A. So which vertices are common for both A and C in this network? D, comma E. Okay, so D has like an edge between both. E also has an edge with both. But this F also has, Karpagama. Yeah, so D, E, F. Good job, Karpagam. Yeah. So only these three nodes are there which have like which lie in the common neighborhood of A and C. So now how do you calculate Adam Adder index? So you first identify these three nodes, and then you just take like a summation over 1 divided by log of the degrees of these nodes. So now that F has a degree of 5, so F will contribute a factor of 1 divided by log 5. Similarly, this E has a degree of 3, so it will contribute a factor of 1 divided by log 3. And this also has a degree of 3, so it will also contribute a factor of 1 divided by log 3. So 1 divided by log 3 plus 1 divided by log 3 plus 1 divided by log 5. And if you calculate this, like you can put this in the calculator and it will come out to 5.62. So does this make sense, Karpagam? Like, so first, whenever you want to calculate atomic adder, first you take the common neighborhood of the vertices, and then just take like 1 over log value, 1 over log degree values of each of the vertex. Okay, it's clear. That's nice. Okay, so then can you tell like what will be the resource allocation index between A and C? If atomic adder is clear, then what will be the resource allocation index between A and C, Karpagam? Just try it on your own, like resource allocation index between the nodes A and C. Yeah, so 1 by 3 plus 1 by 3 plus 1 by 5, exactly. Instead of these log values, you just have to take the actual values. So yeah, good job, Karpagam. Okay, then moving on from local heuristics to like more global heuristics. So local heuristics usually just look at the neighborhoods and something, but global heuristics need to look at the whole the whole graph at once. And one of the global heuristics which is like CAD score, which is somewhat similar to CAD centrality, which we discussed previously. And what this says is that don't just look at maybe the common like don't just look at the common neighborhood, but also look at like uh, beyond beyond one hop distance. Like just don't look at the vertices which are one distance away, but maybe look at the vertices which are like maybe two distance away, three distance away, and so on. But maybe like with kind of a damping factor, like so two nodes x and y are likely to form an edge if they share a common node, but they are also likely to form an edge if they share a lot of like two distance nodes with each other. Like if if x and y have suppose like many nodes of the form z, where like z is two distance away from x and z is two distance away from y, then also x and y are likely to form an edge, even though they don't have some common neighbor. So that's what kind of Card centrality says. It says that yeah, just try to maybe have a damping factor attached, but take all the nodes in, take all the kinds of distances into account. So yeah, so Card centrality is just like summation over p from 1 to, so this Card score is just summation of p over 1 to infinity alpha raised to the power p, and then a x y raised to the power p, where a x y raised to the power p is just number of paths of length p that exist between x and y. So number of paths of length p that exists between x and y, uh, mm, multiplied by this damping factor alpha raised to the power p, and yeah, summation over p from 1 to infinity. This is what is usually called, this is what is Card centrality. So like this is similar to Card centrality. This is called Card score here. So I think like is this clear, Karpagam? Like can I move on from this? Like what is Card score? Okay, it's clear. That's right. And then similarly, we have like a global heuristics like hitting times or commute times, which are more inspired by page rank model. So what do these kinds of things say? So hitting time just says that okay, like suppose you are in a random surfing model. This is like a surfing model which is used in defining page ranks also. There's a random surfer which starts at node x. It moves to a randomly chosen neighbor of x. And so basically, if a node starts doing a random walk, then what's the expected number of steps it takes for the random walk to reach from x to y? And this is what is called the hitting time score. Like in a random walk, what the expected number of steps needed to reach from x to y is what is called the hitting time score. Okay, and yeah, and similarly, what's a normalized hitting time score? It's just maybe like the hitting time score multiplied by like a normalizing factor, which is pi y, which just says that okay, like this ht of x comma y just says that okay, like what's the expected number of steps with which you will reach, in which you will reach from x to y. But like you also need we can one can also multiply this with maybe the probability with which one will reach y in general. So this is kind of a normalizing factor, nothing much. So like normalizing score is like not too different from hitting score, but yeah. But the high level idea is if you start doing a random walk from x, in how many steps will you reach y? This is what this hitting time denotes. Okay. And yeah. So yeah, calculating this kind of a thing is a bit difficult. But yeah, like this can also be done. And similarly, like what is commute time? Commute time is nothing but like general like a symmetric version of this normalized hitting time score. So you take the hitting score between x and y, and you take the hitting score between y and x, and you sum them up. Like this is like normalized hitting score over from x to y, and then y to x, and then you sum them up. Yeah. So this is what you call commute time or normalized commute. So commute time will be just hitting score from x to y plus hitting score from y to x, and normalized commute time will be like normalized hitting score from x to y and normalized hitting score from y to x. Okay, then maybe we can move on to the next kinds of models, which are probabilistical models. Like so, till now we were just discussing like heuristic based models, but now let's just see some uh, probabilistic models. So as we have seen previously also, like What are hierarchical networks? So hierarchical networks are networks which kind of have a hierarchy among them. So there is a set of nodes, and those set of nodes maybe are joined at level one, and those level one nodes kind of try to join together to form some level two supernodes, and those level two supernodes combine to form maybe some level three supernodes, and so on. So that is what you call a hierarchical network, and it can easily be represented as a tree, as we have done, or what is called a dendrogram. Like we'll discuss what a dendrogram, but like it's not the same thing as a tree. And yeah, smaller the height between links of groups or nodes, the higher the similarity. So let's just see what's kind of a dendrogram. So note that you can form hierarchies on your own in the network. Like suppose the graph given to you is this the graph which has this like solid edges between them. So these are the edges which are present in the graph, and then you want to form a like maybe hierarchy or a dendrogram over it. So dendrogram is like for different hierarchical decomposition, there will be different dendrograms. Suppose uh, I say that okay, for the first level of hierarchy is this A and B will be merged together, and E and F will be merged together. So that's what this dendrogram represents. That at the first level of hierarchy, A and B are merged, and E and F are merged. And then at the second level of hierarchy, this merged AB will be merged with C. So this is one second level hierarchy, and nothing else is done in the second level. And then third level hierarchy will be this ABC set will be merged with D set. And then this EF set will be merged with this ABCD set to form this final root component. So this is like one hierarchical decomposition leading to dendrogram D1. Similarly, dendrogram D2 can be obtained by hierarchical decomposition where you say, okay, A and B are merged together, E and F are merged together, and then D is merged with E and F, and C is merged with A and B, and then all of these are merged together. So note that this dendrogram is kind of more balanced, and it's like much better decomposition because it decomposes it puts D, E, and F in the same set, and A, C, and B in the same set. So D2 is maybe a better dendrogram representation than D1 for this kind of a network. And in this probabilistic model, what do we do? So we assign each node in each internal node in this dendrogram network with some probability PR. So each internal node R has a probability PR, which we define, like what's the value of PR. And then for any two nodes X and Y, suppose the nodes are here like A and C, we say that the probability with which A and C will be having an edge between them is just equal to the value of the PR at this common ancestor, at the least common ancestor of A and C. The least common ancestor of A and C here is like this node, and it has a PR value of 1. So A and C will have an edge between them with a probability of 1. Similarly, the edges, the vertices A and D, their least common ancestor is this node, and it has a PR value associated of 1 by 3. So A and D will have an edge between them. So this A and D will have an edge between them with a probability of 1 by 3 with respect to this dendrogram D1. But note that D1 is not the only dendrogram, like there can be multiple dendrograms. With respect to maybe this second dendrogram, the edges A and D will have a probability of 1 by 9 of formation. So note that different dendrograms and different PR values can lead to different uh, probabilities for edges. So what you usually do is you make multiple dendrograms because you don't really know. So in this kind of a graph, like dendrogram D2 is a better representation, but in general, given a graph, you don't really know what kind of a hierarchical decomposition will be better. So what you do is you draw just bunch of random hierarchical decomposition. You draw some n number of hierarchical decomposition, and then maybe just take sum, like to find out the probability, like you kind of take the sum or contributions of all of these dendrograms and then like normalize them in some way. Okay, so yeah, so then this is just a mathematics behind dendrograms. You can just watch the lectures if you want to go into this, but the high level idea is just what I said. And then the last thing which was discussed was in these probabilistic models was these supervised random walks. So know that in local heuristics we incorporated some notion of random walks, right? We said that okay, a random server will assign something like a hitting set score or something, and the better the hitting set score, the higher is the chance of an edge formation between x and y. But what supervised random walk does is it goes along the principle of random walk only, that we are doing random walk, but we'll also take into account like some network topological constraints. So in a random walk, what usually happens is at any point of time, if a surfer is at some vertex v, then it just takes like any outgoing neighbor of vertex v at random and goes there. But in supervised random walks, you take the network topology into account and maybe assign different probabilities to different outgoing edges from a vertex v. And yeah, so for example, suppose there are some positive nodes in the network and negative nodes in the network. Then you take a function psi of xy, which can be any function which like you believe is a good representation for like what kind of what is an important factor in determining like whether x and y should be connected or not. So it's a combination of node and edge level attributes of node x, y, and the edge x comma y. And then like you choose some parameters omegas. Uh, so these are like inherent parameters of the supervised random walk model, and then you train this function f parameterized by this weight vector omega. So in this training network form, like so by training the network, you try to optimize these values omegas over your given psi xy functions and your given positive negative labels. And how do you do this? So you see, so you what we do is we quantify what's the strength between an arbitrary set of vertices, arbitrary vertices u and v. What's the strength between this u and v? It's given by this f of omega times psi of uv. So psi of uv is maybe a collection of like some attributes, and then you maybe take a function which is parameterized by omega over them. So that this is like supervised random walk in its most general form. Like you can have this f omega as whatever you want, as like maybe, and you can pick psi uv as whatever function you want. And there are some functions for which these kinds of things work better. Some functions for which these things won't make sense at all. But the high level idea is this only, that for any edge pair, any vertex pair uv, you define an edge strength between the vertices as alpha uv. And then the idea is maybe like, okay, now you have an edge strength. So now if you are at vertex u, you won't be picking like in a random walk, in a normal random walk, what you do is you pick any out neighbor at random. But here what you will be doing is you won't be picking any out neighbor at random. You will be picking the out neighbor with probabilities corresponding to these alpha uv values. Like so these alpha uv values for a certain vertex v can be normalized by taking the sum, and then you just take the like for any edge uv you just take the f of omega times psi with probability this divide by the total normalization. So this denominator is just a normalization factor to make the probability sum equal to 1, and this is like the alpha uv value. So you take the alpha uv divided by like the normalization factor, and with this probability you take the edge u comma v in the random. So nothing too fancy. Like on a very high level, the idea is just that okay, in a random walk, we go over uh, every edge at we choose an edge at random when we are at any vertex. But if we like associate some kind of weights to all the edges, maybe using Jaccard's score or whatever score you have, then each edge can be weighted differently, and with different probabilities, you will traverse through the edges. So this is nothing fancy, but just a very high level idea. And then you, as we do in random walks, because our like we say that uh, the surfer can randomly restart at some of the node. So then you add a restart probability, which is just then 1 minus alpha times this plus alpha. And then, yeah, then the page rank score is nothing but just finding out the values for these kinds of. So page rank score in on a high level is nothing but the probability with which you will so page rank score for a vertex u is just the probability with which you will be landing on the vertex u, which is just given by like, okay, if you start from some vertex pj, then with what probability will you be reaching the vertex u from j, something like that. So nothing too fancy here, like average and the standard random walk thing, but just in random walks also we studied this random restart. The only new thing added is that you have added some weights to the edges. And then there is this another version of supervised random walk where like what people tend to do is they have some kind of a regularization constraint. So maybe like let's not get into this. So in general what happens is so yeah uh, so you might have some hard constraints like so this thing is nothing but maybe I should not like get into this a lot, but if you're familiar with machine learning, so this term which you add, so in general what you want is you have a like function in machine learning which you have an objective function, uh, or you have a loss function which you want to, let's say, minimize. So here your problem was over these parameters omegas, and then maybe you have a loss function which you would have wanted to uh, minimize over omegas, and that's how you obtain the values of optimal omegas which you should be picking. But note that there might be some kinds of constraints over these omegas and all, and like solving constrained optimization is kind of difficult for us. So what we do usually is we kind of allow constraints to be violated while adding a slight penalty for the constraints being violated, and this lambda denotes that kind of penalty. And like this is what is called like regularization. If you are familiar with like some machine learning ideas, then this is not a very fancy thing, but it's just doing what is called regularization. And yeah, this is just the regularizer term. But if you want to go into a bit more detail, like you can go look at the lectures. Like it was discussed to some extent in the lectures, like not too much, but yeah, somewhat it was discussed. So yeah, uh, yeah, maybe I'll not get into that too much. But the high level idea is this only, that like suppose there are some constraints. So what you want to do is you want to minimize your, like let's say omega square is the optimization problem. You want to minimize this modulus omega square subject to some constraints, and those constraints are given by h of PL minus PD or something. But what you do is like solving this constraint optimization is usually difficult for us. So what we do is we usually treat those constraints as like not hard constraints but soft constraints while adding some penalty term. And now like you have an unconstrained optimization problem. So something like that. Okay, maybe I should not like go into further details. Like you can like look at this from the lecture videos. And now maybe we can move on to the questions. So this is just a straightforward, like just a question which you just discussed. Like supervised random walk is just something which you just discussed. So in a supervised random walk with restart, what does the value AUV for an edge represent? So what do these values? So AUV was these values, which is just f of omega, like f of psi uv parameterized by omegas. So what does this value represent, Karpagam? Like if you have been paying attention, like this is just a straightforward question. Like we just discussed this just now. So for an edge UV, like what does this value AUV represent? Yeah, edge strength. So good job, Karpagam. Yeah, answer is edge strength. So because like this is what specifically we were saying, right? That different edges should be weighted differently because of topology of the network in the random walk. That's why like we have this notion of like associating some
edge strength to each of the edge and then picking the edge in the random walk with that probability. Option A. Yeah. Yeah. So the second question is also like a very generic question, like can link prediction predict missing links in a graph's current state? Yes or no? What do you think, Karpagam? Can link prediction like predict missing links in a graph's current state? Yes, it can predict. So, yeah. This is what specifically is what is called the missing link prediction, right? That you are given a graph and there are some edges missing and you want to predict the missing edges. That is what is called like missing link prediction. And then there is this thing called future link prediction where you are given the current state perfectly and then you want to visualize how the graph will appear in the future state. So yeah. Okay. Okay, so this is something which you should try in the which you should be trying, Karpagam, since you are struggling initially a bit with true positive, true negative, false negative. So yeah. So suppose in a network, you have following samples available. So you have uh, actual positives, you have the set of actual positives, you have the set of actual negative, you have predicted positive and predicted negative, and then you have to find out the accuracy. So Karpagam, you should try this on your own right now. Maybe I'll give you 5 minutes and you can try this out. Yes, accuracy is true positive plus true negative divided by all. But what I'm saying is, what's the value of true positive and true negative here? Like, do try this on your own. What is true? What's the value of true positive? First of all, like, can you answer? Okay, so true positive is 2 and true negative is also 2. So let's just see. So true positive means that our prediction was positive and it actually also it should be positive. So we have to take intersection of these two sets. And what's common? So AB is common between these two and BC is common between these two. So yeah, so true positive will be 2 here. So good job, Karpagam. And let's just see true negatives. So true negatives will be uh, our prediction should be negative and it should be true. So this intersection this. So AD is common, AC is common, but nothing else is common. So again, true negative is also 2. So good job, Karpagam. Yeah, true positive is 2. And what's the set? The set which is common in true positive is like AB comma BC. And similarly, true negative is again 2, and the true negative set is just intersection of these two, which is this AD and AC. AD comma AC. Yeah. And then we need the value of like the total number of predictions, which is true positive plus true negative plus false positive plus false negative. So note that this is nothing but just equal to like total number of predictions which we are doing. So total number of predictions which we are doing is like 1, 2, 3, 4, 5, 6. So this will just be equal to 6. Okay, so false positive is 1, false negative is 1. Okay, so let's just see like
Like you don't so Karpagama, is it going to like actually like although like it's nice that you calculated like false positives and false negatives also for your practice, but in general if you want to calculate this sum only, you don't need to explicitly calculate like these values individually, true positive, true negative, false positive, false negative. You don't need to calculate these values individually, because any prediction will either be true positive or true negative or false positive or false negative. So what you have to do is you just have to take the sum of the total, like you just have to consider the total number of predictions which are done. So this is nothing but equal to total number of predictions. And what are the total number of predictions? So there are three predictions here in the positive set and three predictions in the negative set. So you just have to take the sum of these 3 plus 3, which is 6. Like there are total 6 predictions. So TP plus TN plus FP plus FN will be 6. Although like it's like since we are just practicing right now, so it's good that we calculate all the values individually, because this will anyways help us. But in exam or something, if we are like short on time or we want to do it faster, you can just see that this sum is just equal to total number of predictions. So, yeah. But I just see, okay, so is false positive also equal to 1? Let me just see. So you just said that false positive is 1. So false positive, your prediction should be positive, but it should be false, so actual should be negative. So we have to take intersection of these two sets. And yeah, in this set, BD is common. So yeah, so good job, Karpagam. Yeah, false positive is 1. So similarly, false negative will also be 1. So yeah. So now maybe we can move on to the fourth question. Okay, so like, so this, so this is like the last set of questions for the day. So we are given this graph G, and we have to find the similarity between nodes A and B. And what similarity measure do we have to use? So in the four questions, just Salton index, then common neighborhood, and then Jacquard similarity. So these are the two nodes A and B. So maybe I'll just copy the formulas which were used so that it's easier for you to see. So this is the formula for Salton index. Salton index is nothing but a intersection set divided by geometric mean of the degrees. So note that this size of the intersection set, size of the common neighborhoods will be common in all of these, like Salton, common neighborhood, and Jacquard. Only the denominator, which is normalizing factor, will be different. So maybe let's just see what's the common neighborhood set of A and B. So before all of these questions, like yeah, okay, maybe here only, like uh, common neighborhood set of A and B. So what's the common neighborhood set of A and B? So the vertices which have an edge with both A and B. So D has an edge with both, E has an edge with both, and no other vertex has, like F only has with A but not B, C only has with B, not A. So this is just 2. So there are only 2 vertices in the common neighborhood. So which are yeah, so which are the 2 vertices which are common? So they are D, comma E. Yeah. And then, so what is Salton index? So Karpagam has already written the chat. Like, okay, so Salton index is nothing but okay, maybe I should just write like what's the degree of A here. So degree of A is nothing but 3 here. Like degree of A is 3, and what's the degree of B? Degree of B so Salton index will be just equal to size of the common neighborhood, which is 2, divided by square root. Okay, maybe I should like write it like this. Uh, section. It's like 2 divided by uh, square root of 3 times 2. 3 times 2. So this is nothing but you can leave it as it is, or you can think of it as uh, like root of 2 by 3, square root of whole of 2 by 3. Yeah. So this is the value of salt on index. And is this what? Karpagam is saying that degree of B is also 3. Oh yeah. Oh, sorry. So thanks for spotting it, Karpagam. Maybe I was just yeah. So I was just maybe looking at the network like in a crop version, but yeah. Degree of B is also 3. So good job, Karpagam, spotting that. I also missed it. You also, I think, missed it initially. You wrote also like 3 times 2. Yeah. So sorry. So good fine. So then this is just 3 times 3. 3 times 3. So, so the square root of 3 times 3 is just 3. So this will just be equal to 3 by 3 then. You don't really need the square. 2 by 3. So this is the final answer for salt on index. Yeah, and this is like what you have also written, Karpagam. So good job. And then what's the size of the common neighborhood? So common neighborhood is just 2, because they are like, as we already discussed, they are just 2 discussed in the previous question. Yeah. And then what's the Jacquard similarity? So maybe we can look at the network again. So we know the size of the intersection set. So this common intersection is just this set of vertices, right? This D and E are the common neighbors. And in the Jacquard similarity, the normalizing factor in the denominator is the union of the neighborhood set. So what are the neighbors of A? They are D, E, and F. And the neighbors of B are D, E, and C. So taking their union, you get D, E, F, and C. These 4 you get as the union, right? So union of neighborhoods of A and B is equal to the set C, T, E, and F. And so Jacquard similarity is nothing but 2, like the common neighborhood is 2 and the union neighborhood is 4. So 2 divided by 4, which is 0.5. Yeah. Okay. So does this does the last thing, Jacquard similarity, make sense, Karpago? I see that you did not answer the Jacquard similarity one. You answered the first 2. Okay, it's fine. Okay, then that's nice. Okay, then. So I guess this was it what I had for today. So we discussed some questions related to like the similarities, so 6 questions, and then also like summary of all the lectures of this week. So yeah. So just okay, you forgot the formula. Yeah. So Jacquard similarity formula. I think we have discussed like Jacquard similarity has been brought up, I think, on multiple times, I think, in previous lectures. So that's why I was like, I just remembered it. Like, it's just size of intersection of neighbors divided by size of union of neighbors. So just take the union of neighborhoods and intersection and just like take their ratio. Yeah. Okay, nice. So you remember now. Okay then. So this was it I had for the day. So yeah, so thanks for joining Karpagam, and thanks to everyone who's watching on YouTube. So hopefully I'll see a few more people in person in the next session. So this today's session, so yesterday I had some work, so I shifted it to today, 6 to 8 p.m. But from next week onwards, again we'll be back to like Monday 6 to 8 p.m. timing. So hopefully I'll see you all next week on Monday 6 to 8 p.m. in person. So yeah, till then, I guess yeah. So since no one has any doubts, so I guess we can close the session. So thanks for joining, Karpago. Bye bye.